Hi, I'm Bernard and today I'm going to show you how to build a Raspberry Pi based brewing control using the free Bricks brewing software yourself. The software supports various hardware types such as herms, brew in a bag, mash tuns, or even fermenters. It has a very nice web UI that runs perfectly on any mobile device as well as your PC or Mac and is available from everywhere. The software also supports controlling pumps or agitators, and as the temperature history is recorded automatically, you have a nice log to look at after your brew day is done. As the Raspberry Pi offers an insane amount of flexibility, please feel free to deviate from this tutorial wherever you want. The control we are going to build in this tutorial offers a 7-inch touch display to show the current status of the brew. For example, including temperature history, the name of the current recipe step, etc. The display can also be used to manually control the current brew, for example, by skipping to the next recipe step. 2 temperature sensors that can be plugged in using a 2.5mm micro aux jack. 2 AC outs, one is 16 amps and the other one is 10 amps. 3 DC outs for 24 volts, one of which can be controlled using the software. This one will be at 120 watts, the other 2 will be at 60 watts. There will also be 3 knobs for switching on and off the DC outs, where one knob supports 3 positions, on, off, and controlled by the software. Each DC output voltage can be manually adjusted using a motor governor to control the pump or motor speed. After discussing what you will need equipment and material wise, this video is broken down into the following 6 steps. Skipping to the respective section is possible using the links in the description below. First step is going to be to sketch where we want to cut or to drill. This will take about 3 hours. Second step will be cutting and drilling the housing, which is another 3 hours. The third step will be to install the sockets in the housing, which will take about 4 hours to complete. The fourth step is to connect the wires and do some preliminary tests, which will take 3 hours. The fifth step is building a base plate and mounting everything onto it, which will take about 2 hours. And the last, sixth step is installing and configuring the software, which will take about half an hour. This adds up to 15.5 hours of work. What you will need. To save money, I've split the materials list into essentials and nice to haves that will simply make your life easier. Essentials. You'll need the free Bricks brewing software available from GitHub. I'll put a link in the description below. A housing, I've used one from Excerpt that's 350 by 250 by 150 millimeters. That's 13.8 by 9.8 by 5.9 inches. It cost me about 35 euros. Then you'll need a very long 40 centimeter or 16 inches female to female jumper cable. This connects the Raspberry Pi's GPIOs to the relays for switching on and off the ACs and DCs. Don't fall for the shorter ones. Do not use the 20 centimeter or 8-inch ones. These will be most likely too short. Google for jumper cable female to female. Obviously, you'll need a Raspberry Pi. If you want a display built into your brewery control, I recommend using a Raspberry Pi 3 or later, for example, the Raspberry Pi 4. If you just need a bunch of GPIO, the Raspberry Pi 2 is fine. However, please bear in mind that starting with the Raspberry Pi 3, Wi-Fi and Bluetooth are both included already on the board. Thus, you will save the money for a USB, Bluetooth or a Wi-Fi USB stick. A power brick for your Raspberry Pi will also be needed, as well as a SD card. 16 gigabytes is absolutely large enough. If you have a spare one lying around, just use that one. You'll also need a relay board to control your heating or cooling equipment. A LED power supply, this is your AC to DC converter. I used one from Meanwell that I just had laying around. They will each provide 60 watts at 24 volts. The main DC output is powered by 2 of them, so that adds up to 120 watts. You'll also need a temperature sensor. I prefer the Sonoff TH16 compatible DS18B20 temperature sensor, as these ones have a very nice 2.5 millimeter aux jack. A socket to plug in the temperature sensors. I had 2 AL560 extension cables from Sonoff lying around. I just cut these and recycled the female connections on this extension cable. You'll also need an AC cord with 3 times 1.5 millimeters in square. That's AWG16. Just buy an extension cable and cut it. The DC cord, for the amperages we are targeting, you will also need 1.5 millimeters or AWG16 rating. I've actually used a speaker cable since that has very nice isolation on the outside, and the red and black wires inside are very telling. 2 AC out sockets that will allow us to connect our equipment. 3 AC in sockets. 2 of them are going straight to the AC outs, and the third one is going to power our Raspberry Pi and all DC equipment. We will also need 3 plugs that fit into the aforementioned sockets. I've used C19 ones since they support 16 amp. Continuing with the nice to haves. A display for the Raspberry Pi is a very nice but expensive addition. You can also use XLR sockets to connect your DC equipment, such as pumps and agitators, and also switches and knobs to manually turn on and off your DC outlets. I've started with 2-way on and off switches, but then switched to on and off and controlled by the Raspberry Pi, aka 3-way switches. A drilling machine is absolutely necessary to drill holes into the housing. You'll also need something to cut the housing, for example a jigsaw. You need something to strip the cables. I personally love the Knipex Multi-Strip 10, however a Leatherman will do as well. You'll need a soldering iron and a screwdriver. I recommend going for a bit screwdriver so you can always have the fitting bit. As nice to haves, we have the multi-tool, for example a Makita DTM51Z to cut the housing. Warning: the steps shown in this video should only be performed by experts such as certified electricians. We are dealing with high voltages which can possibly kill you. We don't take any responsibility nor liability for the steps shown in the following. Step 1. Sketching where you want to cut. Think before you cut. In this case, it's actually plan and sketch before you cut. I always try to fit as much as possible into the minimum space. Even if that does not sound like you, I strongly recommend carefully sketching all planned holes as well as the outlines of everything that is going to be located on the housing. Take, for example, the Raspberry Pi display. The required cutout for the display is a good 20 millimeters or 0.8 inches smaller than the actual display. Not considering that will most likely cause collisions with other components unless your layout is really generous with space. Some words about my layout. The front from top to bottom. On top we have the Raspberry Pi display to show the most relevant information about the process. Then we have the 3 DC PWM regulators at the left that can be switched on and off by the switch next to it. The bottom includes from left to right 2 AC sockets for plugging and heating or cooling. The corresponding AC in is located next to it, and 1 AC in on the right side to power all DC outs as well as the Raspberry Pi. Located on top of that, we have 3 XLR sockets to connect DC equipment such as pumps and agitators. On the left, we have the 2 2.5mm aux jacks, as there was no place left on the bottom. One last important note: the cutout for the Raspberry Pi display is not symmetrical. Step 2. Cutting the housing. After we sketch where we want to cut, it's now time to do the actual cutting and drilling. This is certainly the most time-consuming part of the build. Start with the easy holes to get a feeling for the material of your housing. In my case, I went for the holes for the switches. Next step for me was to cut out the medium-sized holes for the XLR sockets. I used a drill saw, one that was rated for metal. For cutting drilling plastic, a wood-grade drill saw is absolutely sufficient. And these come usually in packages with multiple diameters. Fabricating the big cutouts for the AC sockets with a diameter of 40 millimeters or 1.6 inches using a wood drill is a bad idea. I've tried various tools. What worked best was drilling small holes close to the edge and then using a coarse file or rasp to do the rest. Ideally, it's a curved one. Next up for me was cutting the straight edges. Required, for example, for the DC motor governor cutouts and the Raspberry Pi display cutout. The multi-tool from Makita or any other brand will work like a charm. A jigsaw will probably also work, as well as drilling and filing. However, that will be time intensive. A little bit of extra effort was required at the place where the lock is located. My housing had 2 locks. I sacrificed the upper one for the display in favor of a compact layout. Sharp edges can be smoothed out easily using a cutter knife. Other than that, how you proceed will depend strongly on the tools you have available. I've used several drill bits for the small holes, a multi-tool for the straight cuts, display and DC controls, a rasp for the big holes and a cutter to smoothen the rough edges. I cannot stress this enough, the Raspberry Pi display is asymmetrical. The very last sub-step in this step is to peel off the tape. As always, enjoy this oddly delightful moment of peeling. Also, take time to appreciate the final results of this step. Installing the interfaces. This step is pure joy and the reward for the previous plastic chip heavy work. The knobs are very delightful to install. One of the 3 knobs I've ordered had a dead Phillips screw, so I had to reorder it and install it at a later point of time. The only thing you can, and I did, screw up is to mount them in such a way that the Phillips screws of the terminals are not easily reachable. Hint, you can rotate the part that goes into the housing by 90 degrees without changing anything on the outside. The DC motor governors were a bit more finicky. They have a barb that's supposed to snap into place and hold them tight when installed in the housing. Maybe it's my ape brain, but that did not work out for me. The plastic housing was too thick, and I really think every plastic housing will be too thick. So I shortened them and used a longitudinal slot screwdriver to force them into place. This worked 5 out of 6 times, one died, rest in peace, which was replaced by glue. Next thing is the Raspberry Pi display. First, tape the display into place to ease the installment. I'm not sure why, but they did not include any brackets in the packaging that would help to fix the display into place. So you have to build one yourself. Easiest way for me was to build the brackets out of wood since I had a hand milling machine around. Next up, installing the electrical ins and outs, both for AC and DC on the lower side of the housing. If possible, I recommend to connect all cables in the respective components, for example AC sockets, AC in terminals, DC out terminals, before installing the component in the housing. The terminals are generally better accessible when not yet mounted. In some cases, this even is a necessity. In my case, the screw terminals for the AC out sockets were blocked after mounting into the housing. Wherever possible, I've used wire end sleeves or ferrules. In some cases, the result was too thick to go into where I wanted it to be. This was, for example, the case with the relay board, or when I tried to stuff 5 cables into one chandelier terminal. For the AC input terminals, usually crimping is required. However, the cables I've used were too thick, so I had to solder them, which is not optimal since the cable might just heat up, which might cause the solder to melt, your brewing control to catch fire, your house to burn down and you to die. You get the point. Having a shrink hose in place is absolutely crucial to provide at least some insulation to the connector. I've used the same technique for the XLR sockets. Place the shrink hose on the end of the cables, solder the cables to the XLR socket, move the shrink hose to their final positions and apply heat, for example using a lighter. And I recommend to do all of that before installing the socket in the housing. I also gave all cables a fair amount of extra length. You can always cut it shorter, the opposite is possible but more labor intense. The final result looked like this. My awesome construction to expose the DS18B20 jacks using the AL560 extension cable to the outside is a little bit rogue, but it worked pretty well actually. The baseline is that you mill 2 parallel tracks into a thin 5mm or 0.2 inches piece of plywood and cut 2 stripes out of that wood, orthogonally to the milling track. Using a metric screw, I sandwiched the 2 aux sockets in the middle. This holds them into place very good. I think you get the idea by looking at the pictures. To mount the sandwich in the housing, we need to drill 4 more holes. 2 for the aux sockets themselves, 2 for the metric screws holding the whole sandwich in place. Hole drilling was more freestyle in this case. I simply measured the distance of the 2 sockets in my sandwich and marked that on the housing. Connecting the wires. Let's continue with the installation of the DS18B20 sockets. Cut and strip both cables. Cut a jumper cable so that there is some cable left on the female end. Now connect ground, 3.3 volts and the data pins of the 2 AL560 ends with the female jumper cable ends. Refer to the table if you want to decipher the colors of the extension cable. I seriously don't know why the colors are that confusing. You will also need a pull-up resistor for the data pin. This is just a fancy way to say solder a 4.7 kilo ohm resistor between data and 3.3 volts to pull the data pin up. 5 kilo ohm will work just fine as well. Connect it to the pin header as specified in the table. It's important that you use GPIO 4 in this case, as this GPIO is the only one speaking one wire. That's the protocol our temperature sensor uses. Use shrink holes to insulate the cable endings. Now to the bigger picture. The DS18B20 sensors we just hooked up using the non-displayed aux jacks are shown on the right. That part is already done. We continue on the very left with the AC in powering our Raspberry Pi and all DC outputs. Connect the Raspberry Pi power brick to an extension cord and cut that. Connect the loose ends of the extension cords together with the AC-DC converters to a chandelier terminal. With all cables connected and insulated, we can move on to the first test and power up our Raspberry Pi. I roughly checked 42 times and still managed to install my display upside down. If you made the same mistake, have no worries. There's an easy configuration setting to rotate the screen by 180 degrees. Back to the blueprint. The top two AC to DC converters feed their power via the on-off knob straight to the motor governor, which is connected to the DC output. As mentioned earlier, the third DC out from the top on the blueprint is different. While position 1 is the same as with the other two knobs, which is always on, power comes straight from the AC to DC converter, position 2 is new. If set to that position, power has to flow from the one-port chandelier terminal through the relay board to the motor governor. This D route makes it possible to control this DC output using the relay board and ultimately the Raspberry Pi and our software. Speaking of the relay board in the middle of our blueprint, we only use 3 out of the 4 channels it offers. We've already discussed one of them, the DC out. The other 2 are used for controlling the AC outs. To achieve that, the brown L cable is routed through the relay. The blue N and green-yellow mass cables are always connected and go from the AC in straight to the AC out. Also, although not displayed on the blueprint, don't forget to add fuses to your brewing control if you don't have a fuse box outside right next to it. The relay board is supplied with 5 volts. That's the red cable that goes from the most bottom left pin of the Raspberry Pi's pin header, and GND, which is the black cable in the top right pin of the Raspberry. The other 3 cables, yellow, green and orange, are connected to the pins below the ground pin on the Raspberry Pi, which is GPIOs 33, 35 and 37. In this case, you can pick almost any GPIO you'd like, as the Beabout Brick software will ask you upon first start which GPIO you've used to switch on and off the relays. Building the baseplate and mounting stuff onto it. The housing came with a metal baseplate, however I decided to build my own wooden one for 2 reasons. First, mounting the components is much easier when you just can use a self-cutting screw from the top. Compare that to having to mark and drill every hole in advance and hold nuts in place while screwing. Second, I had to create 2 cutouts to avoid collisions with the AC in and outputs. Doing so is easier with a jigsaw than with an angle grinder on metal. Aside from the 2 cutouts to avoid collisions, I only drilled 4 more holes in my new baseplate. These holes are a replica of the holes the original metal one has. The holes are necessary for the screws that bolt the base plate into the housing. I was lucky that the original screws were long enough to still work with my much thicker wooden base plate. Check that in advance if you decide to go the wooden way. Since the lower side of the relay board is not flat because of some dip parts, I've used spacers between the PCB of the relay board and the base plate. I've used Spuck's 3.5 by 12 Z2 screws, which is just meant to serve as an inspiration. As planned, screwing everything into place was a very satisfying, almost dreamlike experience. Installing and configuring the software. Now it's finally time to set up the Raspberry Pi's operating system Raspbian and the Beerbot Bricks home brewing software on your Raspberry Pi. There are plenty of tutorials on the web how to do the first, so I will only cover this briefly. The focus is on the latter. Head over to raspberrypi.org/software and download the Raspberry Pi Imager tool. Now, plug in your microSD card into an adapter and insert the adapter into the USB port of your computer. Wait for the notification sound. You can cancel all dialogues that ask you to format the SD card. Now, browse to the download folder and open the Imager executable you've just downloaded. Follow the instructions to install the tool. Check the box for running the Raspberry Pi Imager at the end. You can also use the search and open it that way after the installation. It will ask you for admin permissions to get full write access to your SD card, which is okay. Select the Raspberry Pi OS 32-bit as your operating system and your SD card as the target. Hit write and confirm to continue. Do not click on Format Disk if that dialog pops up towards the end. Hit Continue and close the imager. Now it's time to insert the microSD card into your Raspberry Pi and power it up. It will automatically resize the file system and reboot. Don't worry, shortly after you'll be presented with a desktop. Use the wizard window to set up your Raspberry Pi. It will ask you for selecting the language, keyboard layout, region and Wi-Fi settings and update the software for you. Do not reboot just yet. Head over to Menu, Preferences, Raspberry Pi Configuration and select the tab Interfaces. Set one wire to Enable. We need this for the temperature sensor to work. After this is done, hit Reboot. After reboot, open the browser called Chromium and Google for Beerbot Bricks Raspberry Pi or browse straight to the GitHub repo URL available in the video's description. Copy the code from the Getting Started section, starting with git clone into a terminal. You can quickly open one using Ctrl, Shift, and T. The setup script will start and guide you through the setup process. The script will ask you for your API key. To get it, open Chromium again and browse to bricks.beerbot.com. After logging in, head over to Brewery, Bricks, and click Add Brick in the top right corner. Copy the API key into your clipboard and paste it in the terminal using Ctrl, Shift, and V. Opening a second terminal and executing pinout might be handy if you are not sure about which GPIO numbers you've used. So I've connected GPIO 26, 19, 13, and 6 to my relay board. GPIO 13 is special since it can do PWM. In your config file, you will need 31, 33, 35 and 37 if you use the same GPIOs as I did. Answer the questions about your setup and hit enter to confirm. You can also use enter to accept the default values. And that's it. This video focused on how to build a brewery control. We will put up another video focused more on the software side of things. If you don't want to miss that, please consider subscribing. Also, this video was pretty time intense to make, so if you liked it, please consider giving it a thumbs up. Alright, thanks for watching, see you in the next one, cheers.